So I'm going to talk about the CHIPS program today and some of the great work being done by our teams. So there's been lots of talk about Moore's Law and Moore's Law's inflection. So let's restate it one more time. So for 50 years, Moore's Law has been all about cramming more transistors into one die, so monolithic, one piece of silicon. And that's been great value to the industry, to the world. But it's come at a cost, exponentially increasing design cost and exponentially increasing fab costs. Just very, very difficult to create one giant piece of silicon that yields. So the question is, what if we can actually break up the giant piece of silicon into tiny, tiny parts, place them very, very closely together, hook them up with a high bandwidth fabric, and do that. That would kind of keep the spirit of Moore's Law alive. It wouldn't be one monolithic piece of silicon. It would be a pseudolithic piece of silicon. So that's the idea of the CHIPS program. So if we can actually pull this off, there are three main outcomes. One, it could potentially extend Moore's Law. As Dr. Su showed yesterday, AMD has been looking at integrating multiple dies within a package, something like 8 different dies, and the cost actually goes down. So as long as the cost of packaging is less than the yield boost you get from the smaller dies, you have a net gain. So what if instead of 8 dies or 10 dies, we could have hundreds of dies stitched together very closely? So that could potentially extend Moore's Law as yield becomes more of an issue at 5 and 3 nanometer. Second, heterogeneous integration. So by coupling these dies very, very closely, we can actually get away from the constraints of monolithic design. So monolithic design is very good for integrating transistors, but it places constraints on IP, materials, geographic location, security, trust, that are troublesome. So we can actually get away from that. And third, design cost. If we actually had an enormous catalog of chiplets, you can actually possibly design an ASIC or a pseudolithic ASIC without having to do a tape out. So we can go from a $100 million design cost and 6 months waiting for the turn on the fab to a few weeks and possibly less than $1 million. Now, to enable this, we need 3 basic technologies. First, we need a standard that would allow these Lego blocks to stitch together. Second, we need state-of-the-art assembly and manufacturing technology. Stitching chiplets together is a lot harder than it seems when you start doing it at 10-micron pitches. And third, if we want this PCB-style design, we need a large catalog of chiplets. So the CHIPS program kicked off in August of 2017, and we're coming up on the end of phase 1. And we've made some great progress in demonstrating that this is definitely the path forward. First one is Intel working with Jariat by the end of the fall is going to demonstrate the world's highest direct sampling RF system by far. And this would not have been economically practical given the diversity of the IP to do without heterogeneous integration. Second, we've demonstrated 1 picojoule per bit energy efficiency for chiplet-to-chiplet communication, and there seems to be a clear path to 0.1 picojoule per bit. Third, UCLA working with industry has shown that 10-micron copper-copper interconnect pillar bonding should be on the roadmap for the industry. Fourth, Intel released this PHY standard as an open source reference design, which is, as far as I know, the first time that's been ever done. And that goes a long way in creating this uniform standard, which is key to the ecosystem. So as you can imagine, this is a very complex endeavor, right? Disrupting a whole ecosystem, lots of moving parts. So we have 2 tech areas. One is the design portion, so looking at existing designs to seeing how can we actually modularize it, right? Can this chiplet-based design approach work in real applications? So we have Intel, University of Michigan, Lockheed Martin, and Northrop Grumman looking at this in different case studies. And you're going to see Intel coming up later to talk about their effort. You can see University of Michigan's poster out in the hallway. And then the second tech area, TA3, is about the supporting technologies that would make this happen. And we have a number of teams. I'm not going to go through all of them. You're free to contact any of the PIs in these efforts if you're interested. But it's Georgia Tech looking at EDA tools, Ferric doing power management ICs, UCLA doing really fine pitch chip stitching on a wafer, ERI Technologies, who just taped out a quad-channel 64 gigasamples per second RF transceiver, which is very exciting. Northrop Grumman building a DDR4 memory controller. North Carolina State looking at a various number of chiplets, RISC-V, AI accelerators, and analog devices looking to see how they could possibly chipletize some of their leading-edge data converters. And so with that being said, I'm going to bring Sergey up here to talk about his work at Intel. Thank you.
Thanks for the introduction, Andreas. Let me share with you two killer applications that were made possible in a partnership with DARPA MTO office. But first, let's start with the Moore's Law. If you get to the third page of the Moore's Law and you get to the section 8, day of reckoning, Gordon points out that, hey, it might prove to be economically more practical to build larger system out of smaller functions that are separately packaged and interconnected together. So what we're saying here is that transistors are scaling, but they are scaling at a slow cadence, and the packaging technology, advances in the packaging technologies and innovation will compensate and will excel the Moore's Law. So once we have this packaging technology, now we can connect the multiple chiplets together, and what we expect out of this system is the same or better performance and functionality. We don't want to give up on the performance in doing so. So obviously, the essential part to this is the packaging technology that offers the high density, low cost, low power, high bandwidth interconnect that can connect all these chiplets together. So what I would like to share with you today is the work that we are doing at Intel in making it possible. First, let's go back to the vision that we presented at ERI last year. So we envisioned the world that had a library of chiplets, that chiplets could come from either us or from our partners, and that could be a variety of chiplets. They could be FPGAs on different technology nodes, I/O, core, memory, accelerators, etc. Then we would have this advanced packaging technology where, just like a Lego blocks, we would put these chiplets together. And just like in the case of a Lego blocks, you obviously need a standard that would connect those Lego blocks together. And what we offered is our commercial AIB interface that we are using in our product lines. And this is the electrical standards that connects over high-density packaging technology. For our demonstrations, we use the EMIB technology, but our AIB interface can work for other interposer technologies. Just a quick refresh on the EMIB. EMIB is the Embedded Multi-Die Interconnect Bridge. It's really a piece of silicon that is inserted in organic packaging substrate. And you can see the cross-section of it on the right-hand side, where in our present generation, we have 4 layers, 2 of which we are using for routing. In the present generation, it's 2 micron pitch, 2 micron width, so we can get 250 IOs per millimeter per layer, so 500 IOs, and the remaining 2 layers we use for the shielding. And if you're curious about the bumping, we can mix and match different bump pitches. So the smaller micro bump pitches at 55 are those that connect to the EMIB bridge, and then conventional flip chip bumping coplanary coexist there. So then indeed now you could actually have a Lego blocks where you put these chips together. As a result, we are not actually limiting to the reticle. We have a programmable platform that now can be as large as the package and can bring all the chiplets together. We can, working with our partners, we can select the best of breed technology available, and we can instantiate it very rapidly here. And in working with partners, we obviously need to explore new business models. Once again, I will show 2 examples, but this is only just the beginning of our journey. So we are seeking the partnership to explore other opportunities. Please just feel free to stop by, and let's just explore the future together. So before I show the examples, let's first talk about the figures of merit. So this chart is the courtesy of Gordon Keller. I borrowed it. It shows the figure of merit over the interconnect. And this figure of merit is the bandwidth density as expressed in the gigabits of data per millimeter of the shoreline of your chip. And it's divided by the power. So the higher the bandwidth, the better. The lower the power, the better. So the figures that are higher on this chart are those that are more preferred. And it's shown, the figures are expressed as the function of the distance that this connectivity solution can provide. So as far as the AIB, it's actually textbook IOSL. Actually, less is more here. So you have tristatable inputs and outputs, you have a data max, and you have a SDR to a DDR conversion. And right now, we've chosen a convenient, robust 2 gigabit signaling. And it's, again, parallel signaling that in a package. The latency at 2 gigabit is actually very low. It's 3 nanoseconds of latency that you can that you incur as you go through it. And like I mentioned on the prior slides, this capabilities needs to be multiplied by 500 IOs per millimeter. Using the 55 micron microbumps, we are burning 0.85 picojoule per bit. So now with this data, you can compute figure of merit, and it comes at 2 gigabit, 500 IOs divided by 0.85, and you get 1.176 terabit per millimeter per picojoule per bit. So that places AIB right there. It can cover about 10 millimeters of distance. And like Andreas mentioned, we made our commercial interface as open source, available for anybody to use. So now, speaking of our commercial roadmap here, here's the evolution of FPGAs. Our last monolithic FPGA was done in 2014. It was ARIA 10. And in 2016, we introduced the first chiplet-based FPGA family. It was 14-nanometer FPGA and the transceiver chiplets attached to it. Shortly thereafter, in 2017, we introduced 2 more types. That first type had HBM memory included, and the other type start mixing and matching transceivers from a different technology nodes and different foundries. This year, we followed with the second flagship FPGA family, Agile-X, that is also chiplet-based. That is obviously have to reuse all the same AIB interfaces that the prior families, so that we don't have to rebuild all these chiplets. We can just take the chiplets from the past and build new set of capabilities. We obviously invested into additional chiplets that we don't have, but now they can be reused across the families. So if we could now take this commercial capability and ride it, and now come up with the new application and new killer application for in the case of DARPA CHIPS program, we thought, wouldn't it be nice if we could get high-end RF capabilities on one side of the device, then we can post-process the data in FPGA, and then we could send it not just electrically, but we could also send it optically. That would be a really awesome thing to do, and can we do it in a short period of time with a low NRE? And this is the sort of 2 demonstrations that I would like to just dive deeper into. So first, like Andreas mentioned, is the partnership with the Jariet. If you want to look under the hood of the Jariet converter that has been presented at GOMAC of 2019, then the next partner is IR Labs. And if you want to look at the hood of IR Labs, please join us at Hot Chips this August. We'll have a joint presentation there. Then we thought this platform also would be good for the university research, so that university researchers could just focus on their value-add capability and connect it to commercial FPGA and leverage all the goodness of the commercial FPGA. And here we have a partnership with University of Michigan on the AI chiplet. So what we have here is a chiplet-based architecture with a library of chiplets that could be transceivers, custom I/O, compute tiles, and any chiplet can be here. So just left to your imagination, and we would like to have more partnership here. Okay, now let's discuss each killer app independently. If you look into the wireless application space, both commercially and in mill, what you see is the following trends. The system are trending to be all digital. You want to have a converter at every antenna element. what matters both commercially and in a mark, size, weight, and power. And we are dealing with this in a chiplet-based approach, but there are obviously alternatives. There are two alternatives to be discussed here. One is the conventional board-level connectivity, where you have a discrete elements and you would connect them via electrical transceiver. Usually it's a GSD standard that is used to connect the devices together, and you would connect them on the board. Alternatively, what some folks did is that they obviously realized that electrical transceiver limits bandwidth and increases the power, so why don't you remove the GSD interface and you select your converter, you select your SoC, and you build it monolithically together. So these are the three options. Let's look at the trade-offs. So first, just looking at the signal path here, and I'm just looking at the state of the art that's available right now. You sample at RF, but your state-of-the-art converter is in the baseband. So you need to have IF stage that would down-convert it to the baseband. Then the ADCs will sample, digitize it, and then they would be sent to the SoC or FPGA for the post-processing through that serial link called GSD. And then in a second bucket, in a monolithic bucket, you could remove the GSD interface, but at that point you would have made the selection of your converter, you would have selection of the function of your SoC, and you would force how many of them you would monolithically do. Yet you are still left with the IF stage that adds noise and distortion, and usually to compensate for the noise and distortion, you would need to spend more power in a converter. We've looked into the market space. Again, was looking for the best of the breed, and we've partnered with Jarrett on their direct RF capability, where their converter can just directly sample and digitized at RF, and we can get either whole bandwidth or the portion of the bandwidth back into the FPGA for the post-processing. We can use this FPGA, we can use different FPGA, we can put different number of converters, so there's flexibility is huge. So how do they all fare up? Let's look just at the key performance metrics. And a sampling rate with up to 64 gigasamples. So this is 6x higher than anything available in the market right now. And it's a higher bandwidth and a higher performance. Speaking of the bandwidth, we are looking at over 25 gigahertz of the instantaneous bandwidth. This is 8x higher than, once again, anything available in the market right now. IF stage, as I mentioned, is not required, so that you reduce size, weight, and power. And the GSD link is also not required in connecting here, so further reduction in the power and complexity. Okay. So here's an example of the partnership with the Jarrett, and Jarrett using the global foundry, and this whole thing coming together as a one solution. We seize the opportunity here to address size, weight, and power in this partnership. So now let's look at the optical here. Sort of going back to the figure of merit I've shared. And I was part of the team in 2011 that actually did the first optical FPGA at Altera. So we've used the micropod technology and used the transceivers to connect it together. And the red dot shows the figure of merit and that this solution could achieve. So then this year we sat and thought, well, wouldn't it not be nice if we had this digital AIB interface just connected directly to the optical engine, no electrical I/O in between, and what can we actually achieve? So what we did achieve is the 3 orders of magnitude higher figure of merit than state-of-the-art optical right now, and 4 orders of magnitude higher than that 2011 FPGA. This is truly innovative connectivity solution now. So imagine you could send the data 2 kilometers away. Imagine you can do it at 1/10 of the power. You could do it at a low latency, and guess what? Your I/O bandwidth is actually higher than the compute bandwidth. This is truly revolutionary for sort of connectivity all-to-all. All right. So in a summary, time for the chiplet is now. Chiplet-based innovation, so chiplet-based solution allowed through this partnership and innovation. We do have all the technology right now to build a solution. And in fact, we are leveraging technology from our commercial FPGAs that are in the market since 2016. Big progress during this 1 year. We have achieved significant milestones here where in this one demonstration, we have optical, direct RF, FPGA, university research, all pulled together. And I really haven't seen anything sort of like this in the market and sort of done in a such short period of time. Second, also chiplet-based FPGA family we are shipping this year. So this is continuous investment from our business unit into the same interfaces. So I would like to invite you for this journey together, and your chiplet can be here, and just think, what can you do with this enormous bandwidth? Can you take advantage of it? If you're interested, here's the link. You can find all the specifications and join us on this route. Lastly, this wouldn't be possible without the partnership between the industry, academia, and the government. Without sort of DARPA strategic investment, Intel would not really do anything like this. I would like to thank Bill Chappell, Dan Green, Andreas Olofsson, and Gordon Keller for their support, and thank you for your attention.